sometimes you don't really have a discrete random variable, right? Sometimes you have continuous random variable. Or in practice, random variables is about whether you are counting or whether you are measuring. But even if you are counting, as long as your sample space is extremely large, then it's just approximately a continuous random variable, right? Just like this example. In practice, it's very common for people to approximate daily bike rentals as a continuous random variable. Well, I am saying approximation. You know it's impossible to be continuous because we are counting the numbers, okay? But because possible values, there are so many possible values, so we use continuous random variables to represent that random variable. Well, that can be more, and that can be easier and more practical. Okay, so here let's try to estimate. Let's try to fit a continuous distribution to this data set. We still start from a frequency distribution, but now we would like to look at the histogram, because the histogram, okay, would suggest us a continuous distribution to fit. Okay, naturally, you would feel that this is very similar to the PDF made by generating uniform distributions. Okay, because you know basically they are the same thing. But anyway, let's go back to here. Given a data set, I first draw the PDF, draw the histogram. Okay, this histogram directly tells me one thing. Data are more likely to occur around the center. Extreme values are not likely to occur. When I see this, I typically have a feeling that, well, this seems to be normal distribution. So later I will try to fit a normal distribution to this data set. Okay, but yeah, we will do that later. So we want to fit a distribution to a histogram. Okay, to do so, we first select a histogram and then use the theoretical frequency for each class to be our estimations. And then we would plot the two sequences of frequencies together. Okay, we will have two sequences of data. One is observed frequencies from the histogram or the distribution, existing data, or theoretical frequencies from our assumed distribution. We have true data from where we observe frequencies, but we also have an assumed distribution from where we get the frequencies that we should see if the distribution is right. Okay, so if the two sequences are in some sense close to each other, then our fitting would be appropriate. Or equivalently, we can draw the PDF of the assumed distribution and using uniform distributions to spread the probabilities in each class when we do the discrete estimation. Okay, so we will still, for example, compare the two PDFs and see whether they are close to each other or not. We probably cannot do it right in the first time, so we probably need to do a few trials and select the best one. And let's see how to do it. So for example, I observe these I observe these black lines. Okay, that's my observed data. If you draw it as a PDF, then it's something like this. Or if you draw it as a frequency polygon, it's something like this. It's basically your histogram, right? Suppose, for no reason, I want to use a uniform distribution to fit into this data set. Okay, then I need to specify the beginning and the ending value. Let's assume that I use 0 and 9,000. Then I can easily calculate the small f for all the possible values. Okay, it must be 1 over 9,000. And then I know where to plot this red line. Okay, because here it's 1 over 9,000. Or I can say, if my distribution is uniform between 0 and 9,000, then theoretically speaking, each class should have exactly 731 over 9 occurrences or frequencies. Okay, in that case, I can plot 731 over 9. Okay, here. And what I want to do is to see whether the black ones and the red one are close or different. Obviously, in this example, it's very stupid to do that because the data set is just not uniform. The probability are not distributed equally within 0 to 9,000. So X does not seem to be uniform according to these two graphs. Okay. On the other hand, I may want to fit a normal distribution to this histogram. In that case, we first need to choose a mean and a standard deviation because with them, I can decide how my normal distribution look like. Okay? You may want to use your own judgment to choose numbers, but a typical suggestion is to use your sample mean and sample standard deviation. So we have that 731 values. We can calculate their sample mean and the sample standard deviation, okay, as around 4,500 and around 2,000. Okay, so we use these two numbers to form a normal distribution, and then for this, we now can calculate the probability for our capital X to be within each category. Okay, from 0 to 1,000, we have a probability. From 1,000 to 2,000, we have another probability, and so on. You know how to get this column because you attended the previous lecture. Okay, X is a normal distribution, normal random variable. You have its mean, you have its standard deviation, you have a lower bound and upper bound, then you are calculating the area below the PDF, or you calculate the CDF of this and that, and find the difference. And you know there are some Excel functions or some other software that you can do to get these numbers. Anyway, once you have the distribution, you know how to get these probabilities. And then multiply these probabilities by 731, you get these theoretical frequencies. If X is normal for this mu, for this sigma, then we expect the first class to contain around 26 occurrences, the second class to contain around 46 occurrences. That's the meaning of this column. Then again, we can plot the observed things and the theoretical things together. The black lines construct the PDF of our observed frequencies. Okay, so this is according to our observed frequencies. And this is our normal curve, right? Or if you talk about frequencies instead of probabilities, this black one is the frequency polygon, and the red one is the frequency polygon based on theoretical frequencies. Okay, and you want the two curves to be close to each other. I probably cannot say that it's a perfect fitting, but this looks much better than the uniform one, right? Because the overall differences seems to be smaller. So I can say that this normal distribution better fits our observed data. So if I really need to produce an estimation, I probably will say that, yeah, I can estimate the daily bike rental to be a normal distribution whose mean is around 4,500 and the standard deviation is 1,900. That's something I can do. Of course, further trials or some personal adjustments are always possible. So, a quick summary. We want to estimate the probability distribution of a random variable. That's what we want to do here. When the sample space is small, just count the relative frequency for each possible value and assign it as the probability. When the sample space is large, you need to group data into classes, and that means you need to have a frequency distribution. Use the relative frequency of each class to be the probability for the random variable to be within that class, and then either use class midpoint or uniform distribution to fit each class. Finally, when the sample space is extremely large, it's typical and it's better to use a continuous random variable, continuous distribution to be our estimation. First, look at your histogram, and that gives you some hint about the potential probability distribution. Then you construct one and find the theoretical frequency for each class. And then you have two sequences. You have observed and the theoretical frequencies. Compare them and stop when you are satisfied about the overall difference, when you feel that they are close to each other enough. Now, in the future classes, we will talk about how do we define small with some scientific approaches. But anyway, at this moment, just use your own intuition and just do a few trials to report one estimation that is having small differences from your observed frequencies. Human judgments are always needed, and you need to do some adjustments by yourself. But this is the general rule for using old existing data to estimate a probability distribution. Okay, let's stop here. Thank you.